Okay, so we'll end with Rodrigo telling us about linearity in a lazy setting. Thank you.
Right, hello everyone. I'm Rodrigo. Me and Bernardo, Toninho, who's there, wrote lazy linearity for a core functional language, and here we are. So linear types, you've all seen them before. Here are two very quick examples. We have a bad function, highlighted in red. Say a linear function, its main properties that it consumes its argument exactly once. So on the left, we have a bad linear function that takes a pointer, must use it exactly once to produce an IO action. This example, it takes the pointer and then frees it twice. So this function is rejected. It's definitely not linear because pointer is being used twice at runtime. On the other hand, we have OK, which is also a linear function from pointer to IO unit. It takes the pointer, frees it once. It's all fine, so this function is accepted, and it is in fact linear. So right off the bat, I want to get a question, and maybe a show of hands for this function, and the question is this function linear? And this is an interesting function which is linear from pointer to IO unit. It takes a pointer, it let binds baz to free pointer, then it does some condition. In the true case, it'll return baz, which is the let bound value, and in the other case, it will just free the pointer. So perhaps we can have a show of hands for whether this function is linear. Do you think that it is linear? Is pointer being used exactly once, is the question. Right. So perhaps not many people are convinced, and I want to answer with, it depends on the evaluation strategy. So if the function is being evaluated strictly, then baz is evaluated right away. We evaluate free pointer right away, bind the result to baz, and then in the event where we have, where we get into the else case, we'll be freeing the pointer again. And in that case, it just surely isn't linear because at runtime, pointer is being used twice. But if this program is being evaluated non-strictly, say with lazy evaluation, we will just bind baz to a thunk, which would free pointer if it is evaluated. But if it's not evaluated, then all is fine. So in the true branch, we would return baz, therefore evaluate free pointer, we'd free the pointer once. In the else case, we just free the pointer. Baz is unused, and therefore we never compute free pointer twice. We have just, at runtime, used pointer linearly. The problem is that there's no type system that can see this. Right, so as far as we know, all type systems will just reject this program. And that's because traditionally, linearity is just too syntactic or too strict. And so the lazy semantics of linearity, which appear with lazy evaluation, are just rejected. A key observation is that syntactic linearity is not necessarily the same as semantic linearity, at least under a non-strict language. So you could say, fine, we just type linearity strictly, why do we care? Okay, so of course we want to be able to be flexible, we want to accept more programs. Linearity is already somewhat burdensome to work with, and if we could just accept more programs as linear, that'd make our lives easier. But there's also a very real-world problem in which a real-world project, which is GHC, the Glasgow Haskell Compiler, in which this problem occurs. So, as you know, we have linear types in Haskell for a while now, and linear Haskell is desugared into this core intermediate language. And core is both lazy and linear, which is, not all languages are both lazy and linear, but core is. And core is optimized over and over again, and this changes the structure of the program a lot. Of course, core is typed, and that serves us very well because we can use the type checker as a source of sanity checking for the intermediate language and the optimizations that GEC does. If it type checks still after, it's probably fine. But linearity is just currently ignored altogether in core because we'll see. It's because of this problem that because laziness and linearity are currently just not understood by type systems statically. And of course, if we don't have linearity in core, then we also can't use it for optimizations. That's something that'd be cool to do. So it's just, this advantage is not to be able to type programs like this one. So linearity is just dropped. As soon as we get to core, we just ignore it completely because optimizations destroy the syntactic linearity very easily. We have an example here where we inline let y equals free x in y, So y is in line, and then we have let y equals free x in free x. And this is already problematic. Maybe we drop the binder afterwards, but we type check all intermediate results in the program. And this one is already rejected before we even have the chance to drop the binder. Because y, again, is not used and core is lazy. In our paper, we have this type system which does accept the lazy semantics of linearity statically. We've got a soundness proof over this instrumented big step semantics that tracks resource usage at runtime. So the soundness proof over our type system also guarantees that a well-typed program will consume at runtime resources linearly. And we also prototyped it as a GHC plugin, which we introduced into the core pipeline of GHC to try and type check every intermediate program, and we had very good results. But on this talk, I want to focus on the core ideas for typing linearity in the lazy setting statically. So first of all, lets. And lets are the simplest to handle. We have the same program that we saw before in the introduction. And note, resources in the lets are only consumed if the binder is evaluated. So let's try and type this. The key idea is, okay, let binding doesn't consume resources, so we're just not going to consume resources in the typing derivation. Instead, we'll annotate the let variables with the resources that were used in its body. So y here, we have let y equals free pointer. So y is annotated with pointer because that's the resource that we have. So I'm just going to type this example. We have two contexts, the unrestricted context to the left side of the semicolon, and we have the linear context. So variables in the linear context must be used exactly once, and the others can be used as many times as you want. And then we want to type the full let. So we use pointer to type the binder, and okay, that type checks. And now we do not remove pointer. So in traditional linear type systems, you'd have to split pointer either to the binding or to the body of the let. In this case, we just have it in both places. But we also introduce y annotated with the pointer resource, and then when we use y, it'll consume pointer indirectly. So this is how linearity is in a traditional linear type system. We have two contexts. We have one linear context split into two to type the let. We use the first part of the context to type the first expression, and we use the second part of the context plus the variable that was bound to type the second expression. So you see, delta 1 went to one side, delta 2 went to the other side. They never are reused. And now compare this against the typing rule for let in our system. We have the same context splitting. We use it to type the expression which is let bound, and then to type E2, we still have both parts of the context. We don't consume delta 1 at all while typing the let binder. And now we introduce y unrestrictedly. And it's important that y is unrestricted because we may want to drop it. We could just use x directly, and we could just use delta 1 directly, and so y can just be dropped. But if it is used, then it'll consume the linear resource. That's what it looks like in the variables rule. So this is for traditional linear variables. We also have this rule. So if you want to type an x, and you have an x in the linear context, you just use it. Now if you have an annotated variable, you want to type y, and y is annotated with delta 1, then the linear context must be exactly delta 1. That's that there. Right, so lets are easy because they don't do any evaluation, only at its use sites. Cases, on the other hand, drive evaluation, therefore that makes them slightly more, considerably more subtle. So I want to go through a couple of examples. We have pattern matching on a tuple, which is already evaluated. This is just x, y. We match on a and b, and then we do something with both a and b. This is already accepted in linear Haskell. This is accepted traditionally. But now here's something else which is kind of similar, but is already rejected by traditional type systems. We match on x and y, we bind a and b, and then we do something with x and y and ignore a and b. Well, this is fine because x is just y. Sorry, a is just x and b is just y. They're the same program. This is highlighted in yellow because our type system accepts it. Now here are totally not fine programs. We evaluate. We scrutinize free x, and scrutinizing an expression forces its evaluation to weak heteronormal form. So we scrutinize free x. That'll surely do something to x. And now we use we try to use x again. That's not fine. Here's a second example in which we use X somehow, and then we match on V and ignore V. That's also not fine, because use could be identity, and if use is identity, now we're just ignoring X in the continuation of the let. So this is also not fine. We must make sure to consume the matches if we have a non-weak head normal form expression there. Yeah, case expressions drive evaluation, consuming parts of resources. So the idea for typing lets, one of the main ones, is that we have to have two different rules based on whether the scrutiny of the expression is or not in weak head normal form. And this is a static property as well. So in this case, this is the same example. X and Y is in weak head normal form, so we type it differently to this expression which is not in weak head normal form. Again, these programs may seem stupid. No one would want to write them, but the compiler will just produce tons of them, and we must be able to type them. Right, so for weak head normal form cases, it's easier because we know that the weak head normal form will match one of the patterns. So here X and Y will match linearly to both A and B. So we will just do the same thing as a let, because the bound variable in the pattern is not going to be evaluated. So we just have A is the same as using X and B is the same as using Y. And so then when you use X, Y, that's fine because A and B were introduced in the context similarly to the let. So yeah, we have X and Y, X and Y types the scrutiny, and then we still have X and Y, and we now have A and B which have these aliases, this list of resources. And now you could either use A or B or X or Y. Well, you have to use both X and Y or A and B, or A and Y, or X and B, so you can do this kind of combination, and it'll all be accepted. So we're just trying to delay as much as possible, consuming the resources. Now, for not weak head normal form case expressions, the resource is just going to be used, really used, so we have to do something about that. And the way that we do this is by introducing the variables which are used in the scrutiny as irrelevant in the continuation. So that looks something like this. We have X here. X is used to type the scrutiny. And now the continuation is typed with this irrelevant X that's annotated in brackets. So an irrelevant variable cannot be instantiated with a variable rule. So you just will never be able to use this irrelevant X directly at all. But if you have a variable which is annotated with an irrelevant X, then you can consume the irrelevant X through this variable. That looks something like this. Typing the continuation with an irrelevant variable. This one is rejected because we don't have X in scope. This thing is irrelevant, so you can't use it. Typing this is going to be a problem because now you're ignoring the irrelevant X, which is consuming the rest of the resource, right? Here, you still have to make sure that V is consumed. And that's what this irrelevant X is doing. You have to use it because this is a linear variable. You just can't use it directly. So how do you use it? By using V. Right, in the paper, as I mentioned a few slides before, we have a soundness result over a linearity-aware semantics that guarantees us both soundness and that well-typed programs do consume linear resources exactly once. We also have a large set of optimizations that GHC does, and we prove that if the program before optimization was well-typed, then optimizing it results in a well-typed program as well. So that basically ensures that our system is able to accept most of the transformations that GHC does, at least all the ones that we checked, and one more which is slightly more difficult to analyze, and that is in the paper. And we have also the GHC plugin, which had pretty good results. Right, linear core, which is the name of the system that we introduced, accepts more of the lazy semantics of linearity. Not all of them. There's some future work like multiplicity coercions, which go into where coercions and multiplicity mix. And it is suitable, this type system, for the lazy linear core language because of all the results about optimizations and the GHC plugin results. Of course, so I've been focusing a lot on linear Haskell and Haskell, but this should apply to other lazy linear languages. Not many of those exist, but it also applies or can be made to apply to strict language which have strict features, strict linear language with strict features. Yeah, right. That's what I have. Thank you.
And we have quite a bit of time for questions, so I'm going to have any to start us off with. Yes.
Thank you for the talk. So I was curious about the small technical detail. So you showed this nice, compelling example for irrelevance, but it seems to me you could have solved the same problem by promoting the binder to be a linear variable itself. So is there a reason why you didn't do this? Is it just to have a unified treatment of binders?
If you promote the variable to be linear itself.
Could we go back to the example?
Yeah, no, understood.
So V could be introduced as linear here.
Mm-hmm. V could be introduced as linear here. I want to say that I'm sure that I thought of that, and that's something that I don't recall exactly now why it's more complicated. Yeah, I would have to think more. At the moment, I don't recall. I would hope that that's not so simple. But I think there's something more complicated here, but I cannot think of it off the top of my head.
Okay, thank you.
At the beginning, you said that one of the things that you want from this is that for optimizations on core to take advantage of linearity. Do you have any examples of new optimizations that on core that can now take advantage of linearity?
Mm-hmm. Right, so there's a handful of references to this throughout the literature about optimizations, and it's often just a side comment which says, well, if we had linearity, then, for example, inlining, we didn't have to depend on heuristics. You could just use the linearity information directly. So that's one example, inlining. Yeah, that's the best example, I think. So inlining is heuristic, but if you have linearity, then you just know it's used exactly once. That's one example. But the other ones are future research. I think it'd be interesting to explore how linearity can be used for optimizations. It's currently not at all. You don't have linearity in core.
Thanks.
We've got a quick question from online, which is, did the GHC plugin find linearity bugs in GHC?
Come again, sorry?
Did the GHC plugin find linearity bugs in GHC?
Did the GHC plugin find linearity bugs in GHC? That's a very good question. Yes, so the GHC plugin accepted the vast majority of programs that were produced by GHC, but not all. And the not all is the interesting part. Which programs are linear core rejecting? So some of them are technical details, like a rewrite rule, which is rewriting things which by ignoring linearity. So you take a linear function and then some rewrite rule is just dropping the linearity information, and that is not allowed. It also saw how multiplicity coercions are necessary for some programs. And did it find any bug? I don't think so, but I didn't analyze all of the programs that failed because, yeah, it's a few dozen. And some of them could be real bugs. But very important to note, the GHC should not in any way, no optimization should ever be destroying linearity. It's very good that it doesn't. Because it'd be very weird if you wrote a source program which frees X once and then the GHC optimizer makes it so that it's freed twice. That's definitely not okay. Yeah, so as far as the plugin is concerned, I didn't find any specific bugs, but I found programs which were rejected by linear core, which hinted at real, what do you call it, limitations of, say, rewrite rules, for example, how they were defined. Yeah.
Question up there.
Hi, I had a question on the first example.
First of all,
the let y equals free x in if.
Mm-hmm.
So I can imagine like another way to write this program is, or like to compile this program or type check this program might be like let baz pointer prime equals free pointer prime, and then when I use baz, I sort of pass in my linear value baz pointer.
Yes. So today, if you wanted to make this program type check, you could make pointer an argument of vaz. Is that what you're saying?
Yes.
Yes,
like
so that would be valid in linear Haskell today. Yeah, it'd be good if you can accept this directly, though.
Okay, thank you.
Thank you.
I had another question about this example. This might be a misunderstanding of my knowledge of Haskell, but could you use baz twice here on one of the branches? Do let things only get evaluated once if you use them twice?
That's a very good question. Right. So so what happens if you have a thunk which frees the pointer and returns unit. So the first time that the thunk is evaluated, it'll use and free the pointer, and then bind unit. And then unit is fine. You could, in principle, just use the unit as many times as you'd like. And but what if the thunk is ID of x? And now forcing ID of x just returns x again. And then you don't really know. So here's one place where you have to be conservative. In principle, if it's lazy and not call by name, then at runtime there might be programs which you would reject, which would be fine because the thunk would be evaluated to something which had fully consumed the pointer, but you can't know statically if it is fully consumed. But that's a very good question. Thank you.
I have a question. So is there any program in your GHC plugin that is semantically correct with terms to linear types that you reject? So sort of, I guess, have you proven completeness?
Mm-hmm. So is there any program that appeared in GHC core in the plugin that my system rejected, but is still semantically linear? Yes. So, I keep thinking about this, but one of them was the rewrite rules. So you had some rewrite rule which made use of linear things in as far as the type of the function which got applied, it wouldn't be linear just because the function is unrestricted and is being applied to a linear value. But that would just be, at runtime it's fine, but it's, at the type system it doesn't check. Again, the example with the thunks, like if you have a thunk which fully consumes a linear resource and returns some unrestricted thing, that unrestricted thing could in principle be used multiple times, but you can't check that statically.
Thank you.
Is that a question at the back? No. Okay. Okay, I think we'll leave it there. So I think the next thing is lunch. So let's thank our speaker one last time. And